We're going to talk about a extremely simple theorem that has a really powerful consequence in quantum information and quantum computation sciences. It's called the no cloning theorem, and this is particularly interesting given the fact that in classical information sciences, info sciences, cloning or copying is pretty much the the majority of the reason why these we value these information sciences so highly in the first place. So let's say I have this information encoded in terms of this string of bits. Okay, and let's say this is song I particularly like, and I can make a hard copy of this on a USB and give it to my friend or my little sister to listen and enjoy the same song that I enjoy. So let's say this is song copy, and this is what we do literally a day in and day out with the existing information that I have, for example, on my hard drive. And you can sort of think of this as my classical wave function, although there's nothing wavy about this. Anyway, this is my classical state of the song, and this is my clone. And I can easily make a clone of the original content of the song. There one doesn't think too much about this copying process because this is something we take for granted, in at least in classical information sciences. However, it's quite funny that this sort of thing cannot happen in the quantum information sciences, and the proof of these impossibility of a cloning of a quantum information is done via an extremely simple argument, which I'm going to present to you. So the argument sort of goes by contradiction. That is, suppose we had a good cloner. Okay, that is, I have this operation that will copy the existing quantum information to a kind of a blank tape or blank hard drive or external drive. And the role of an existing drive that already had this information about the song encoded is some kind of a wave function or state. Okay, so this is roughly the analog of a song in the classical information medium, and the blank tape or blank USB is the other state that has basically no information at all, because all of the qubits in that sector is set to 0. Okay, so the existence of a good cloner means there exists some sort of unitary operation which can turn such an existing state into this state. That is, the information contained in this first wave function has just been faithfully copied to the second state here. Okay, so that would be a pretty good definition of a cloning mechanism or a cloner in the quantum information sciences. And the proof that I'm going to present is going to convince you that such a unitary matrix simply cannot exist. And here's why. Now, using this cloning machine, I can clone the information contained in this wave function I call psi1, or since this is sort of a universal cloning machine, I can do the same thing with a different wave function. Or I can do it with their linear combinations. Maybe I should take care to normalize the state. Now what gets copied is this wave function, so I should be careful to write down both the left-hand side and the right-hand side of the tensor product as a linear combination. Like this. Okay, but when you do this expansion, you have 4 terms that arise. Psi1 times psi2, psi1 times psi1, psi1 times psi2, psi2 times psi1, and psi2 times psi2. Okay? Now, let me do a perfectly valid operation on this whole expression. Because unitary operation is a linear operation, I can just do this unitary operation individually. Like that. Because this wave function is a sum of 2 terms, I can express the result of the unitary operation as the sum of the unitary operations on the individual terms. Okay? Now, when applied to each of these state, the result, according to the definition of my universal cloning machine, would be this. So here psi1 gets cloned to the right-hand side, and here psi2 gets cloned to the right-hand side. Now, so we started from this expression, and by following one perfectly legitimate manipulation, we arrived at such an expression. But following another perfectly legitimate operation, we arrived at this expression. So then these 2 expressions better be the same. But it's clear that these 2 expressions cannot be the same. Right? It's just impossible that for general wave functions psi1 and psi2, these 2 wave functions would become identical. That's just not going to happen. So what was the problem? The problem was that we assumed the existence of such a universal cloning operation, and the fact that we arrive at this contradiction implies that the assumption was wrong. That is, such a universal cloning operation simply cannot exist. and still remain consistent with all the rules of quantum mechanics. Okay, the rules of quantum mechanics essentially being that the rules of all the linear algebra and the vector space apply to the quantum states and the operations on such quantum states. Okay, so although this argument is really simple, it puts a powerful constraints on the sort of things that one can and cannot expect to do with the quantum information processor. Okay, and therefore, this statement is elevated to being one of the most important theorems to keep in mind in quantum information theory.